This section will provide an essential understanding of the key parameters and the characteristics of the battery system. Now that we understand the individual cells and we know what is its working principle, we can see how these cells are assembled into modules and pack to create a complete battery system. This assembly process usually happens in several steps, are shown over here. We start with individual cells, whether these cells are prismatic, pouch, or cylindrical, and no matter the chemistry, the cells are stacked and they are fixed in a module tray. The stacking configuration of this model is going to be carefully chosen based on the applications and the space requirements that we may have. Once we have all the arrangement of the cells fixed, then we proceed to do the electrical connections of those and to create and form the battery module. This model might include also some supporting structures for mechanical stability, for instance, a housing of the module, and even sometimes some thermal management systems to extract the heat out of the module. The modules are the intermediate steps that allows the battery design to be simplified and in general to simplify the design by grouping those cells. Once we have the module, then they can be combined to form the battery pack, which will incorporate, besides of the module, different systems, like for instance the cooling systems, connectors, and also for instance the battery management system that will be monitoring the modules and the cells in the packs. This modular approach makes it easier to scale up the system for different applications, from very compact electric vehicles to large grid storage solutions. All of those uses this approach. When we are building the battery system and when we are stacking these modules, the connections of the cells are going to be crucial for achieving the desired voltage and the desired current capacity. This is accomplished through two types of connections. We can do serial connections or we can have parallel connections between our cells. The cells, when they are connected in series, the objective of that is to increase the voltage of the battery. In this case, for instance, the total voltage of the module will be calculated by the number of cells that are connected in series times the cell voltage. And it means, for example, if we have one cell, for instance, NMC cell that has a nominal voltage of 3.6 volts, and we connect 10 of those cells in series, at the end, the total voltage of the string will be 10 times 3.6. It means that it will be 36 volts. On the other side, we have the parallel connection, and the cells connected in parallel will increase the current capacity of the battery. For instance, in this case, the current of the module will be equal to the number of cells that are connected in parallel times to the rating current of one of those cells. If we connect, for instance, 5 cells and each of the cells have a capacity of 2 amperes hours and they are connected in parallel, then the total capacity of our module will be 5 number of cells connected in parallel times the capacity, 2 amps hour, equal 10 amps hour. In a battery pack, these principles at the end can be extrapolated also. So when we are connecting multiple modules, we can connect them in series or in parallel. And based on that connection, we can achieve the required system voltage and the required system capacity. So it's gonna be, the pack voltage is gonna be equal to the number of modules that we have connected in series, multiplied by the voltage of one of those modules, and the current of the pack will be equal to the number of modules that we have connected in parallel times to the current that each of those modules can provide. Let's continue defining also the C rate. The C rate is a very common term that we can see, for instance, in the datasheet of the batteries. And it defines how quickly the battery can be charged or discharged relatively to its capacity. we can only relate the C rate with the current that it is referring to once we know what is the capacity of the cells. So if we have a battery and this battery says is noted at 1 C rate, means that the battery will be fully charged or fully discharged in 1 hour. If the same battery we then doubles the C rate, so we have 2 C rate, it means that it will double the speed that we are charging or discharging. It means that we will be completing the process in half of the time. It means 30 minutes, for instance. On the other side, if we have, for instance, a C rate of 0.5 C, it will slow down the process, taking at the end 2 hours to fully charge or discharge the battery. As I mentioned, the C rate is gonna be relative to the capacity of the cell. If I take a battery of a capacity of 5 amps hour, 1 C will be equivalent to a current of 5 amps. 2 C will be equivalent to twice that current, it means 10 amps, and 0.5 C will be equivalent to half of that current, it means 2.5 amps. Then let's see the energy density. And the energy density is a parameter that measures how much energy a battery can store relatively to the volume or the weight of this battery. So when we talk about the energy density, usually we have to specify either it is volumetric or gravimetric energy density. In the case of the volumetric energy density, it is the energy that is stored relatively to the volume, and typically it is measured in watts-hour per liter. On the other side, the gravimetric energy density will be measured in watts-hour per kilogram. A higher energy density means that the battery can store more energy in a smaller or in lighter package, which is critical for portable applications, and also it is going to be critical for electric vehicles, since the performance of the vehicle will depend on the weight of the vehicle itself, and also the energy density will give us some ideas of how efficient is going to be that. If we look at the cell and the characteristics regarding the voltage, we have the nominal voltage and the open circuit voltage. Let's start with the one in the bottom, the nominal voltage. This is a key parameter for designing the systems that are powered by batteries. As we saw previously, the voltage on the pack and the module is usually calculated based on the nominal voltage, and it refers to as the average voltage of the battery under typical operating condition. It is used to describe the battery's standard operating condition, and it is often a rounded value. So we can see, for instance, that most lithium-ion cells has a nominal voltage that will be between 3.6 or 3.7 volts. This value will depend strongly on the chemistry of the cells. And even though the actual value voltage will fluctuate during time and with the use, we use a constant voltage here, on a rounded value here. On the other side, we have the open circuit voltage. And the open circuit voltage is the voltage of the battery when we don't have current flowing. As you can see here, for instance, that the terminals of the battery are not connected to anything. So it is very important. It's a very important parameter because it helps us to estimate the battery state of charge. And the open circuit voltage, or OCV, represents then the electrochemical potential that the battery has, and depends entirely on the state that the battery has in a given time. As there is no load connected to it, it means that it's the state of the battery without being affected by any external factor like, for instance, loads, resistance. So at the end, this will provide us with a true snapshot of the energy that is being stored in the battery. A full charge battery will have a OCV that is gonna be larger than the battery than the OCV when the battery is discharged. For example, if I take a lithium-ion cells, we can have an OCV of 4.2 when the battery is fully charged and 3 when it is almost empty. On the opposite side, we have the closed circuit voltage. So this is the battery voltage when it is delivering current or when it is connected to a load. It is gonna be always lower than the OCV. And the reason because of that is because the model of the cell has an internal series resistance, as you can see over here. And when we connect the external circuit, once we have a flow of current through that internal resistance, we will create a voltage drop that will cause a difference in the measurement between the OCV and the CCV. Great, so let's move now to some terminology on the state of charge, state of health, and the depth of discharge of the batteries. Those are parameters that at the end help us to monitor and to manage the battery performance and give us an idea of how is the use of energy being managed in the battery. So before jumping to those definitions, let's see some general parameters that we can define based on the figure over here. And let's start then with the battery's rated capacity. That is this. Over here. The rated capacity of the battery is gonna be the total capacity that the battery has, and the capacity the battery was designed for. So it means that is also the capacity that the battery has once it is completely new. It represents the upper limit of the energy that the battery can theoretically store and can theoretically deliver. As we use that battery, what happens is that it will degrade over time. So on red, we are showing also the degraded capacity that represents the portion of the battery capacity that has been lost due to aging, to the repeated cycles, and to the normal uses of the battery. Considering that degradation, then we also have another parameter that will be the maximum usable capacity. This is going to be then the actual energy that the battery can store and can deliver at a certain time. As the battery degrades, or when the battery is completely new, the maximum usable capacity and the rated capacity will be the same. As the battery is being used and the degradation takes place, the maximum usable capacity is what we can actually use out of that battery. Now that we have those initial definitions, let's see what is the state of charge and how it is calculated. So the state of charge will indicate us the percentage of the battery that is available relative to the maximum usable capacity that we have. And it will be acting as a fuel gauge for the battery, showing how much energy is available and how much energy we can use. It is calculated then as the available capacity split by the maximum capacity and multiplied by 100 to have it as a percentage. So for example, if we have a battery and this battery has a maximum usable capacity of 10 amps hour, and currently we have available 7 amp hours, it means that the state of charge of that battery will be 70%. A battery that has a state of charge of 100%, it means that the battery is full, and a battery with a state of charge of 0% represents a completely empty battery. Then we have the depth of discharge. And the depth of discharge will indicate us the percentage of the battery capacity that has been used or that has been already discharged relatively to the maximum usable capacity of the battery. So it's going to be the opposite to the SOC. How we calculate it is going to be 100 minus the state of charge, SOC value. It is very important, this parameter, because this focus on how much energy has already been consumed, and basically for the battery cells it is recommended to have that consumed battery within a certain range that can extend significantly the battery lifetime. So keeping the SOC within the 20–80% will avoid high degradation of the battery. Another critical parameter for understanding the performance of the battery is then the state of charge, the state of health, sorry. The state of health helps us to measure the current condition of the battery compared to its ideal or new state, and it is expressed as the percentage of the battery original capacity. So it will depend on the rated capacity, and it will be the maximum capacity that we can take out of the battery divided by the rated capacity times 100. The SOH reflects how much capacity has been lost over time due to aging, due to environmental factors, for instance, high temperatures, and it's very important since monitoring this degradation helps us identify, for instance, when the battery is approaching the end of its usable life, and will also alert us when we need to replace that battery because of any safety concerns also. Now let's discuss the cycle and the cycle life of the battery. Those are two metrics that measure how batteries are used and how long they can last. A cycle is referred as one complete process of charging and discharging the battery. And it's one complete process to its full capacity. So we can think of that a full cycle will be to start with a battery that is 100% SOC, it means a full capacity, discharge it till 0 and then charge it again, and that counts as one full cycle of the battery. But we can also have, for instance, partial cycles that also count. For example, if we take a battery and we discharge it from 100 to 50%, then we charge it back to 100, that will count as half of a cycle, and if we repeat this process twice, we will have one full cycle. This will help us to count how much we have used that battery, and it will be used to also know from the cycle life that will be defined later on how much cycle we have already executed. So at the end, the cycle life of the battery is the total number of cycles that the battery can perform before its capacity will fall to a specified percentage of its original capacity. For example, in that case, as it is shown here, if we have a lithium-ion battery that have a cycle life of 1000 cycles, this would mean that this battery cell after 1000 cycles will degrade to 80% of its original capacity. Some of the factors that affect the lifetime of a battery and the cycle life are, for instance, the type of discharge, the operating temperatures, and the C rate of the battery. Let's bring all of those concepts together by examining an example of a battery cell datasheet that we can see here. These are the nominal specification of a Samsung battery cell, NMC, with this reference. As you can see, usually the manufacturer of the cell will provide us with the rated discharge capacity, also give us the charging voltage, the nominal voltage, how the battery has to be charged, What is the method? In this case is constant current, constant voltage. What is the standard current for charging? What is the maximum current for charging? What is the maximum current for discharging? And in this case it will be a different rating for continuous currents and for pulsed or not continuous currents. We also have what is the lowest voltage that the battery can have, the cycle life of the battery, the weight of the battery, and the dimensions. As you can see also, for instance, when the rated capacity is being presented, they tell us as well what is the conditions of testing for that capacity. In this case, the battery has a maximum and standard discharge capacity of 4,900 milliamps, and this capacity is obtained when we do a full cycle of a battery, charging it with a current of 0.5 C. As we saw previously, a current of 0.5 C means half of the capacity. So if the capacity is 4,900 and we multiplied it by 0.5, we get the current that they are using for charging it. In this case, the battery is going to be charged until the voltage of 4.2 volts is attained. And after that, once the current has dropped below 98 milliamps, then they say that the battery has been fully charged. And then they start the discharge process with a current of 0.2 C until the voltage reaches the 2.5 volts. And at that point, they assume that the battery has been completely discharged. Out of this, we can, for instance, see and calculate what is the energy of the battery. As you see, the capacity, we can take it directly from the datasheet, and the energy will be calculated by the capacity multiplied by the nominal voltage of the battery. This is the nominal energy of this battery cell. And in the same way, we can also calculate, for instance, the energy density. That will be the nominal energy of the module of the cell that we just calculated, divided by the weight of the cell. Using those cells, then we can create modules and packs. In this case, we have an array of 14 cells in series and 8 cells in parallel, using the previous cell that was specified. As you can see here, the pack voltage then can be calculated as the nominal voltage of one of the cells multiplied by the number of cells in series that is specified here. The pack capacity can be calculated as the nominal capacity of one of the cells multiplied by the number of cells that are in parallel. That will be equal to 39.2 amperes hour. And the energy of the pack can be calculated as the capacity multiplied by the voltage of the pack, as can be seen over here. Additional to this, we can also calculate the energy density of the full battery. That it will be equal to the energy of the pack split by the weight of the pack. As you can see, the energy density is slightly lower than that the battery cell had initially. This is because once we fabricate the pack, we need to include some additional elements, for instance, the enclosure, the insulating materials, the connectors, and so on. And all of that adds an extra weight and reduces the energy density of the full system.